This lesson includes a brief overview about the final positioning of fibers. That is to say, in this lesson we will talk about distribution and orientation of fibers, how can we measure and how do the most influencing factors affect, at the end, the structural capacities of fiber-reinforced concrete. It is well known that concrete is weak in tension, and a way of improving this characteristic is adding certain types of and amounts of fibers. The latter, which are randomly positioned, might provide some additional residual strengths to the concrete element when it bears tensile or flexural stresses. Since fibers are by definition randomly added to concrete during the mixing stage, the position and orientation of each isolated fiber depends on the pouring process, formwork geometry, and rheological properties of concrete. For both steel and polyolefin fibers, residual strengths are directly related with the number of fibers crossing the fracture surface. Such number of fibers crossing certain section is related not only with fiber distribution but also with fiber orientation, as will be explained in this lesson. Moreover, some other effects on fiber positioning may also take place, enhancing or worsening the results, as can be seen in the pictures. In the case of plastic fibers, they can even be folded in the surface and thus without any contribution in fracture. In absence of any action, the random distribution of fibers would suppose an isotropic distribution of fibers. Nevertheless, isotropic conditions may only occur in an idealized situation in which use of concrete is not feasible. The general performance of concrete permits the production of an evolving material that provides the advantages of a fluid mass in the initial stages and strength in the hardened state. Thus, the presence of physical boundaries during the setting stages is needed in order to shape the final element as desired and is a key factor for the final positioning of fibers. Summarizing, anisotropy in concrete production can be shortened in the following significant lines: wall effects and pouring and compaction processes. So, the question appearing is how to measure fiber orientation and distribution. The positioning of fibers has been assessed by using stereological tools, statistical ones, and using methods such as CT scan, X-ray, optical methods, and even methodologies which seek to imitate concrete by using translucent fluid with same rheology. Some others exploit the electrical properties of concrete in measuring real angles. However, beyond research studies, the most commonly used tools regarding the orientation of fibers is the combination of the manual counting exercises and the so-called orientation factors. As previously suggested, in an ideal positioning of a straight fiber and considering the rotation from its initial point, the fiber would be lost in the counting when it rotates 60 degrees inside the vertical plane, because it would not reach the cut surface. The theoretical number of fibers that cross any section would, at the end, be obtained by means of expression 1 in red. This number of fibers would enclose the theoretical number of fibers to be counted in any section. Once the theoretical number of fibers in an idealistic positioning has been defined, the next step is to denominate the orientation factor as the relation of the number of fibers counted in a certain surface over its theoretical number. That is to say, it is possible to obtain the orientation factors once has been counted by using the expression 2 in blue, with A being the cross section of the sample, AF the section of one fiber, and N the number of fibers actually counted in situ. Such expression was firstly introduced by Krenzel in 1975. From another perspective, long fibers would be placed in a straight manner and could be cut in a proportional number, being located at the end of the fiber length. Hence, the theoretical numbers of fibers to be counted in a shown surface cross-section is not related with fiber length, but with volume fraction and the fiber cross-sectional surface. That is to say, if all the fibers were perfectly oriented perpendicular to the fracture surface, the orientation factor would take the value 1. In the opposite situation, as depicted in the slide, the value of the orientation factor could become 0. The examination of the existing models has reviewed several of the most relevant research proposals that deal with such issues. Note that these models consider the fibers as rigid fibers, and subsequently some new approaches must be done for the use of macrosynthetic fibers. Having said that, DuPont and Van der Waal estimated by numerical integration the values of the orientation factor in 0.5, while Sorossian set the isotropic value in 0.405. Concerning wall effects, DuPont and Van der Waal estimated by numerical integration the values of the orientation factor in the lateral bands of a size of half the fiber length, such as 0.6. The figure in the slide shows the areas of the differential orientation factor that also included a square of size half fiber length in the corners, with a value of orientation considered as 0.84 due to the existence of two boundary conditions. The model also computes a final orientation factor combining such values weighted in proportional terms to the corresponding fractional surface. This is in accordance with experimental evidence and models, with a small band of values that range between 0.42 and 0.82 in the experimental data. Moving on to the axiom of self-compacting concrete, Laranjeira provided one idealized model to be considered for the use of self-compacting concrete that was to consider the flux of self-compacting concrete taking place in virtual layers of thickness equal to the fiber length. Therefore, if such boundaries are considered, the value of the orientation factor in the bulk is the same as that assumed for the presence of one wall, close to 0.6. Research has confirmed that steel fibers, due to the table vibration, tend to orientate along horizontal planes. However, the vibration does not have a significant effect on orientation if the specimen is only vibrated for 1 or 2 minutes. It was not clear if consolidation performed by means of external vibration due to the low density of polyolefin fibers might migrate upwards towards the free surface. Research using these tools showed that this floating effect does not take place. By means of a fractured surface analysis, most of these issues can be addressed. As can be seen in the slide, in the case of polyolefin fibers, it is relatively easy to count and even to measure the number of fibers broken or pulled out in a fractured surface. Other surfaces can be counted by showing the element in several positions, as depicted in the slide. This procedure can be seen in the supplied video regarding orientation of fibers and permits drawing maps of orientation factor. With such results, it is possible to localize the effects of sources of anisotropy by making the required variations in the pouring methods, compaction procedures, and specimen sizes. As an example, some results are shown in the following slides. This slide helped to conclude that there was no floating effect in vertical elements due to the external vibration. In the case of self-compacting concrete, due to the absence of a standardized filling procedure of the molds, several specimens filled from the sides and other from the center showed that by means of fracture tests there was no effect, and it was not possible to localize that the filling of the molds had any effect. And by means of the analysis of the fracture surfaces, it was possible to localize that the filling the molds from the center overestimates the residual strength of the fiber reinforced concrete. Moving on to a long element, such as a structural beam with polyolefin fiber reinforced concrete, the orientation maps allowed concluding that the flux increases the orientation factor with more effectivity in longer beams than laboratory specimens. Note that in this case, the lateral walls had been removed to assess only the action of the flux of self-compacting concrete. The following bibliography is suggested, as well as the video supplied in the course. Thank you for your attention.